All right, let's work another optimization problem. A rectangle has its vertices on the x-axis, the y-axis, the origin, and the graph of y equals 4 minus x squared. In the first quadrant, find the maximum possible area for such a rectangle. Okay, as we remember, the first thing we want to do is try to draw a picture to describe what's going on. So I know that I have, I'm going to draw a rectangle where my vertices lie on the x-axis, the y-axis, the origin, and this graph all in the first quadrant. So I'm constrained to over this side, this quadrant right here. So we know what the graph of y equals 4 minus x squared is. It's the graph of a parabola that is concave down. We know that it crosses the y-axis at 0, 4, and that it crosses the x-axis at 2 and at negative 2. But I'm not so worried about negative 2 because that's not part of my constraints. So I have the parabola opening down this way, and if I were to continue drawing it, would it be, I'm going to just do a dotted line because we're not going to use it. And I have this rectangle that's inscribed inside like this, where its vertices lie on the y-axis, the x-axis, the curve, and at the origin. I just don't know where it lies on the y-axis and where it lies on the x-axis and where it lies on this curve, and that's kind of the heart of this problem. So we want to find the maximum possible area of such a rectangle. So let's label what is changing, and that, or what we don't know. And so x, this distance right here, because I don't know where it lies on the x-axis, I'm sorry, how far it goes out on the x-axis, and we'll say this distance right here is y. And what we want to do is maximize the area of that rectangle. That pen doesn't work so well, so let's get a different color. And we know the area of the rectangle. Let's try this one. The area of a rectangle is equal to the base times the height, so x times y. All right, and so this is the function we want to maximize, and these are our two unknown variables. So this is a problem that we have of too many variables, because remember, we want to be able to write area as a function of one variable. So that's when we go look for a relationship of our two variables, and we have one. We know that this right corner is going to lie on this curve, and this curve is described by y equals 4 minus x squared. All right, so this is the relationship between x and y. So whatever x value I have and whatever y value I have, that point will lie on this curve and will be related that way. Okay, great. So that means I can replace my y with 4 minus x squared. Let's move up into this corner. So the area, which is now going to be a function of x, is equal to x times, instead of y, I'm going to write 4 minus x squared. Yay! I might simplify this so I don't have to use the product rule, but instead can use just the power rule. And so I have area equals 4x minus x cubed. Now I'm trying to maximize this area, so I'm now going to take its derivative with respect to x, which is 4 minus 3x squared. Now remember, when solving these optimization problems, I set the derivative equal to 0 and solve for when it's equal to 0, and then I also think to which values in the domain of a are such that the derivative does not exist. But as you can see, there are none because this is a polynomial and it's defined everywhere. So now I need to solve this problem, but this is a quadratic. So I know that 3x squared equals 4. Let's move this up. And so x squared equals 4/3, which means x equals plus or minus the square root of 4/3, or 2 over the square root of 3. Now, I don't care about the negative solution to this quadratic because I'm stuck in the first quadrant. So what I know is that x equals 2, still in the window, over the square root of 3. All right, so that's the x value that maximizes this area. But that's not what the question asks. The question asks for find the maximum possible area. So I need to now take this value